So here, the goal of basically clustering is to represent the data via clusters. So you can see that we can easily identify different clusters here, and clustering algorithm, they are fully unsupervised, which means we don't have ground truth. Okay, so what we want is basically for K-means particularly, we have a set of data points, and we want to, let me use different color. So we have a set of data points, x1 to xn, and we want to assign each point to what we call a cluster centroid. So if this is the centroid of this cluster, we want this point to belong to this centroid of this cluster. And if this is the centroid of cluster 2, we want these points to be assigned C2, for example, okay? So the number of centroids here are we have C1, C2, and C3. So basically K is equal to 3. So we have only 3 points. What does that remind you of, guys? Somehow we're trying to get or learn the centroids, right? So the C matrix. So we're trying to decompose or factorize X into a multiplication of a C and a W somehow, right? So, like in the factorization process, it means that it's a multiplication of 2 matrices. And this is what we have been doing so far, starting with one representation and trying to factorize it into into two, and one of them would be learnable. Sometimes the C is learnable, other times are, and both of them are learnable, right? Cool. So now let's keep going with K-means. So just a kind reminder here. So we denote the set of indices of the points belonging to the kth cluster as Sk. Okay, so Sk saves all the indices of points xi if they belong to the cluster K. Very simple. Now the centroid is represented or defined as the center of the cluster. And since it is defined as the center of the cluster, we can easily express the centroid of cluster K as an average, okay, over all points xi belonging to the cluster K. So it's the average, it's the center. So as you guys can see, it's almost the center of these points. Now, what we want to do through this, if we want to learn the CK, we are after what we call AI. So what is AI? Is actually a cluster assignment index. So we want to minimize the distance between each point xi to ck. So for example, if I have these kind of, let's say, if I have these points and let's say this is C2, okay? But if my estimation of C2 is right here, if I estimate this point as C2, what do you guys notice? That the distance between my point xi and C2 is very large compared to this distance, right? So what happens here, basically, we are in a very bad optimum, which means this center is not really good. It doesn't minimize my distance to the center that I am searching, all right, of the cluster. So it's an optimization problem, the same thing. And here, what we want to optimize is the distance between each center and its, corresponding point. And by doing so, we're trying to identify this, assignment. So here, basically, it tells you that this point xi belongs to which clusters. So let me give you an example. So a visual example, very simple. So we have a bunch of points. Let me use a thicker line. So quickly. So we have a bunch of points here, other points there. This is the centroid. Okay, another centroid. And then I want basically, so this formula is telling me that for a point xi, right? So this is my point xi. I'm going to calculate its distance to the 2 centroids. So I have 2 centroids here, C1 and C2, right? So this is C1 and this is C2. And then I'm going to select the assignment based on the minimum distance. So the minimum distance is achieved with C1. So AI is equal to what? Is equal to C1. All right, so I'm assigning it to cluster 1. So that's what it means. So I'm taking the minimum. This is what it means, argmin, minimum over the number of clusters, cluster centroids. All right. So basically here, what we want to do is, we want to, like find the centroid, and this distance right here, if we want to minimize, it's an average of intra-cluster distance. Intra-cluster distance, what does it mean? It means we want each, like point to be close to its centroid CKA. So if I have a bunch of points here, I want to minimize these distances, right? So these are my points, and the sum of these distances, which is within the cluster, that's why we call it an intra-cluster, within the cluster is minimum. So if I had a very bad assignment and I had some points over here and I assign them to the same cluster, I'm not going to minimize. So these points will increase the intra distance, because now the radius of the intra distance was this, let's call it, for example, delta 1. But in the first example, now if I include wrong points, I'm going to have delta 2. So the intra distance, the average intra-cluster distance, is very high, which means that these points should not be assigned to this cluster. All right, so you guys understand that. Great. So now let's move next. So here, this is an alternative mathematical formalization using basically clustering. So clustering can be formalized as a minimization problem, a matrix factorization problem particularly, where we factorize out X onto a multiplication of two matrices C times W, and these are to be learned such that, so it's a constrained optimization subject to Wi belonging to EK, K1 to big K. So what is EK? Basically, it's a basis vector where EK is equal to 1 and the rest is equal to 0. So if you take position, small k here, this is 1, the rest is equal to 0. So let's see why this formalization works. Okay, so you guys can think about it and think about dimensionality. Look, so everything is beautifully summarized in this figure. Okay, so what do we have here? We have 3 centroids. We have the red, the green, and the blue. And here, let's say we have the original data. So D, so this is D times K. Okay, so D times big K. And then this is, our C spanning matrix. So this P spanning matrix that we are after, which is actually our centroid. We want to discover the centroids. The centroids represent the new basis, right? So these are the new basis vectors, and they belong to D times K. All right. And then what we have here, so actually we have a matrix, an assignment matrix W. W belongs to R K times N. And what we want to do, we want to reconstruct or represent the original data X, all points, every single point that belongs to D times, so here, every single point, D-dimensional point, we want to represent it as a combination of these. So what does it mean? It means if I take, for example, this point right here, I want to reconstruct it. So I will reconstruct it as a multiplication of these basically points, right? So we take the C, the first one, and I take the, I take the third column, right? And then put the first value right there. So you do it one by one, and then the second, and the third, right? So here, basically, what is this telling us? It's telling us that I'm trying to represent, if this point belongs to the red one, right? It belongs to this red cluster. I should be able to define it as a multiplication of these, you know, like of the C times the W, the weights. So, however, this is a constraint optimization. Why it is constrained? Because at the end, I want the W to take only one value. So for all points, for n points belonging to this cluster, which is the red points right here, I want them to take one. For the green points, so these three, and then the structure of the W that I'm learning is very unique. So I wanted actually to include all these points. So when I multiply by this C, I can approximate it. So I can reconstruct these points almost very well using these centroids and the neighboring points, actually. So you guys can take some time to think this through, but this is, you know, a nice formalization of clustering algorithm using matrix factorization, where we're trying to learn a special format for the W, and then a special also, and a more kind of relaxed format for the C. So moving up next, so here is how K-means works. So it's basically here, you guys can see an animation. We're trying to find the centroids. We're starting off with a particular random optimization with a random initialization of the centroids, and we optimize until we get some good clusters towards the very end. So great. Now we reached the very last part, which is the generalized matrix factorization. So matrix factorization can be formalized as into this, you know, using this loss optimization function, where we're trying to learn the coordinate weights for each vector, the new representation in the new spanning space. And here we use the Frobenius norm because we're doing matrix multiplication. So these are matrices, not vectors anymore. So the Frobenius norm is just simply the squared norm of all elements inside that matrix. That's how you calculate it. It's actually the squared Euclidean distance, basically, right? Like in using L2 norm, it's the generalization of Euclidean distance to matrices. Or Euclidean norm. And ideally, we want CW to be equal to X. So X is factorized into a product of two matrices. And here, if we look at this example, so we have, if we have the C, this is our C, right? It's D times N, so this is our X, the original data. We want to factorize it into two matrices. And then the first one will be D times K. So you guys can guess. So it's D times K. This is the spanning vectors times what? It should be K times N, right? So K times N, it will be something of this order. So you have small vectors, actually K, like this, and then times N, and this is the weight vector, the W, that we want to learn. All right, so this is the matrix factorization problem, and you factorize it out into two blocks of matrices in this way. So PCA, we have seen that PCA is a factorization problem where CW is almost equal to X. And then here for the matrix completion recommender system, we also have seen that, but we added the constraint on the omega because we only have the ground truth values inside the omega. So we optimize a loss over the ground truth values of the ratings, for example. We have seen also that K-means can be formalized as a matrix factorization problem where we want to approximate X by a set of centroid vectors and their assignment matrix, basically, okay? And now we have also what we call sparse coding, which is a generalized version of K-means. So basically, what is sparse coding? Sparse coding is considered as a more general version of K-means, where data points can belong to multiple clusters. So in clustering algorithms, one data point will be assigned to only one cluster. So here with sparse coding, one data point can belong to multiple clusters. Okay, so this is very interesting, and it's the same formalization. The only difference that we change the constraint. So the constraint here is that the norm, the sparse norm or the L0 norm, this is called the L0 norm of W, okay, L0 norm of W, which is the sparsity norm, is smaller than S. So basically what this constraint tells us is that the number of non-zero entries in the assignment matrix WI, okay, is at most S. So if you look at this, if you have an assignment matrix, if we go back here, and if you have your assignment matrix with, let's look at this example. Where was it? Okay, so I'm gonna just draw again. So I think it's easier to show you here. So what it's telling us is that if I have a WI for a point XI, so I want to know this point belongs to which cluster, right? Or to which clusters. So before in K-means, we only had one value and the rest are zeros, right? So this is the constraint that we had, which means this point can only belong to cluster K of centroid CK. Now with sparse coding, we have a different constraint, which means the W will have a lot of zeros, but only S, entries will be non-zero, okay? So basically, here we'll have, for example, this is, we can have 0.9, lots of zeros, 0.8, lots of zeros, and 0.7. So what does this tells us? It tells us that S here is equal to 3. So I'm allowed to, my point is assigned to these clusters, cluster 1, cluster, for example, K, and the last cluster, big K, right? So my point belongs to these. I can represent my point Xi as a linear combination of 3 clusters. The centroid of cluster C1, CK, and C big K. It's a linear combination because I am using multiplication, right? So I'm multiplying this. So the rest of the values are set to 0. So we don't take into this into account, and you can guys verify this with if you write this manually, and I really encourage you to write this manually. And this is what we call sparse representation. Sparse representation, it means the majority of the values are set to 0, and only a few samples can help me represent my data. Okay, so that's what it means. And you guys can see that also sparse coding and sparse representation is a matrix factorization problem. So the last one is non-negative matrix factorization. So which means we can factorize a matrix X into CW such that, or subject to, C and W positive. So it's non-negative factorization. And this is used everywhere. So it's used also for the matrix completion that we had in the recommender systems. So it means that the data is non-negative. For example, you have text data or pixel intensity of images. So basically the data is not negative. So you cannot allow for these to be negative. So both of them need to be positive in your factorization. So the last part, just to summarize quickly. So matrix factorization problem is, formalized as a multiplication of 2 matrices. And this is to represent the original data. And we have seen different examples. So the first one is we have principal component analysis, which is a linear encoder. And we have C is orthonormal. So in this case, C is orthonormal. Recommender systems, we don't have any constraints on C and W, but X is only partially known. That's why we do have the omega here for computing the ground truth, right? And K-means each column of W is a standard basis vector. So standard basis vector, it means, you have 1 and lots of zeros, and you have 0, 1, lots of zeros, etc. So only one element is, one entry in the vector is allowed to take a value 1, the rest is set to 0. The next example is sparse dictionary learning or sparse coding. So each column of W is sparse, and this is what I explained. So basically, a lot of values are 0 and a few are non-zero, right? And these non-zeros, non-zero values that represent, they allow the data point xi to belong to different clusters. And then the non-negative matrix factorization, so the constraints on C and W is both of them should be non-negative. All right, cool. I think we reached the end of this. It's been a long lecture, I think. Yeah, so 3 hours, 40 minutes. It's about that. Yeah, very good. You guys survived. Do you have any questions? So look, I know that you got a lot of this, but also a few, you know, I think, as I mentioned, next time I'm going to go over all of this, especially here with beautiful illustrations explaining, you know, all these kind of cases together, encoding, decoding, you know, with some matrix multiplication. So we're going to revise this and, you know, like having a good, you know, representation of this whole first lecture in high resolution. All right. Do you have any, and we're going to see also how to represent these as neural networks, which is so exciting, like just, you know, graphical computational graphs for representing these linear algebra formula. Anything